Let's just do full view.
Yeah, sure. How do I learn to compute?
Things happen
Yeah.
all the time. Okay,
Right.
your turn.
Great.
Okay.
All right, great. And feel free to ask me any questions at any point. It's pretty informal, so just interrupt me if you'd like. Okay, so I'm going to go ahead and get started. So here's the overview of this talk. The first part of this talk, I'm going to talk about some work I did with this wonderful reporter, Hiroko Tabuchi. I don't know if you guys have seen some of these articles regarding the airbag recalls about and Takata and the sort of all those issues associated with that. So I sort of worked with her and sort of tried to help her try to do her investigative reporting a little bit more optimally using machine learning. So I'm going to first sort of talk about that. I think that's sort of an interesting story. The second part is going to go into more about the kinds of problems you deal with when you're a journalist and you are when you do like something like a FOIA request, which is a Freedom of Information Act request, and you get these huge document dumps. And so oftentimes you don't journalists just don't have the time and energy to go through all of these documents. And then in that case, how do you go about a way of actually dealing with these large document corpuses? And so one way of doing that is to apply something called a topic model. Just to get a sense, how many people know what a topic model is here? Okay, so that's a pretty good number. Okay, how many people have actually? What's that? Right. How many people have just actually applied it to a problem they've been working on? Have you guys? Okay, great, awesome. Okay, so yeah, so they're super useful. Part of what I love to do is I also love to build web apps. So, and part of the problem with topic modeling or some of these models is that, sometimes they can reside in a toolbox somewhere that you have to sort of spend a lot of time understanding how it works. And so before I came to the New York Times, I was working on a way of creating a web app that allows you to sort of just do literally upload a bunch of files. And so if you guys actually want to implement this or try to download this web app, and you have your laptops on, feel free to download two things: the VirtualBox and Vagrant VM, and then you can actually run your topic model by just uploading a bunch of files, and then it has this nice D3.js visualization and all that stuff. So I can talk more about that kind of stuff too. And then I'll talk about some future directions, and if there's extra time, I'll talk about some interesting extensions to topic models and things like that. Okay, so let me just go ahead and get started. Right, so here's the story of the faulty Takata airbags. So this has led to a huge recall, about 14 million cars, much bigger than the GM recall. Some of you might be familiar with this sort of ignition switch problem. And one of the things that Hiroko did in terms of trying to figure out this story was that she basically, there's a database, the National Highway Safety Transport Authority collects a bunch of these comments about how these accidents happen. And there's about 33,000 of them actually when we're sort of looking at this data set. And that's a lot of comments. And so the problem is, how do you go through all these comments effectively? Because what's inside those comments are sort of certain scenarios where the sort of airbag issue might arise. So there's complaints about, oh, my airbag inadvertently deployed. Oh, something happened. I was driving to the CVS and all of a sudden my airbag exploded. And those are the kinds of things that Hiroko needs to find and follow up on in order to better understand, what is actually happening when it comes to this airbag stuff. So one way I was trying to help her was, well, you can develop a prediction algorithm that can predict whether a comment was suspicious or not. And so the idea is that you're going to use this data set and you're going to try to discover features that are representative of this sort of suspicious comment. So this is a supervised problem. You have some labels that are suspicious and some labels that are not suspicious. And that's sort of the general approach. Okay. So here's a sample comment. February 25th, key would not turn on. Took 10 to 15 minutes to start. So there's a bunch of text here. Right? And so the typical procedure when you sort of think about these things and you want to maybe try to do some kind of prediction off of whether something's suspicious is you sort of want to featureize this. And one thing you can do is you sort of tokenize all the words. And so one way of doing that is you have new, Toyota, Camry, LE, da-da-da-da. You break these into these individual words, or you can break them into bigrams. Okay? And so after you break them into bigrams, you get this enormous vocabulary of all possible words and possible biograms, word combinations. And then you can then filter it and say that, okay, well, if it doesn't appear, if this particular biogram doesn't appear more than a certain number of times, let's just remove it. For this instance, we just sort of removed it if it appeared less than 5 times. Okay, so this is just basically just doing some straightforward data cleaning. We're just trying to extract some interesting features here. Okay. So it turned out actually, when I did this, I got about 56,000 features. So it's a pretty large feature space. I mean, there's larger, but 56,000, it's pretty formidable with about 33,000 comments. Okay. So I should mention that Hiroko did an enormous job of actually labeling close to like 2,000 comments or so as being suspicious. So that was sort of my training set. And so you take a subset for training, and then you have a set for testing. And after you train on on your training set, you can then sort of figure out how well you do on the test set. So this is some straightforward cross-validation. Okay, so here you just have a matrix of word frequencies, or basically how many times did that unigram or bigram feature appeared, and you have these labels, and that's all you're pretty much doing. You're just sort of taking this, looking at this, doing some cross-validation, and then sort of training on your test set, and see how well you do in terms of predicting once you train on your test set. Okay. Okay, so when we did this, for this particular experiment setup, I held out 25% of the suspicious and not suspicious comments. So I tried to maintain the bias in the test data set. You do this about 5 times, so you create random splits with the same bias, and then you keep retraining the model with these splits. And it turns out when we did this, if you sort of average across your ROC curves, you get basically pretty high accuracy, something like 0.97. And why? I mean, so 97% accuracy is great, but I'm getting 97% accuracy on comments Hiroko already saw. She already knows that these comments are suspicious. So the sort of interesting question, or one interesting question, is what is the ones the algorithm thought was suspicious, but she didn't label as being suspicious? And so that was sort of what I was trying to do this for, because I didn't think it would actually do this well, but it did this well. And so you sort of want to look at that sort of 3%, or the point sort of 3 on the AUC, and sort of see which the algorithm was like, oh, I think this is actually a suspicious comment, and it wasn't part of this test set. Does that make sense? And so when you do that, those comments are the things that are potentially worth checking twice. Okay, so so here this is just basically average over 5 fivefold cross-validation. Regularize that. When I say regularize at 0.3, I just mean there's a parameter that you can specify this to determine how much sparsity you want in your features. So here I use an L1 regularized logistic regression. Okay, so people who are familiar with that, that's just sort of a way of penalizing your supervised learning algorithm. So you want to make sure you have that regularization set up. And it turns out that if you look at this, it's sort of interesting because you see that some of the most, interesting features are words like suddenly deployed, inadvertently, burned, deployed, things like that. These turned out to be highly, highly predictive. And the things that are very predictive of normal comment, things like Mercedes and Volkswagen, was also interesting of itself, which show that certain car brands actually did not deal with this sort of Takata issue maybe as much. And so we looked at these comments, and Hiroko did a careful look at some of the comments that she, and we found about 374 of these out of the 33,000 that was sort of stuck out. So she already looked at a whole bunch of these, and we had like a few days left to actually get through this. But it actually turned out from those comments she missed, there were 7 new cases where a passenger was actually injured. So there was a whole bunch she checked. And there was a whole bunch relevant to airbags and inadvertently, but even following up and calling each one of these people of the 374, which she actually discovered 7 more cases where people were actually injured from that was highly suspicious and due to, most likely to these faulty airbags. Okay, so this is just an example of how you can use machine learning to aid journalism. It's a very straightforward, example of using something like logistic regression, regularized logistic regression, on an interesting data set to get some really interesting insights and solutions to a problem. And if we did this earlier, we could have probably, Hiroko could have saved a lot more time. Instead of actually hand labeling 2,000 of these comments, she could have probably done a much smaller subset, and I would have been able to find a much, something like that, find those other comments relatively quickly. Okay? Okay. All right, so before I move on to the next thing, any questions about that?
Can you maybe just explain suspicious comment versus normal comment?
Oh yeah, so a suspicious comment is basically something she labeled as thinking it's suspicious. So things that she thought,
Relevant? What she is relevant?
yeah, relevant to her for the
So it's
Takata
a good way
airbag.
suspicious.
Yeah, good way suspicious. Sorry, not as in like, whoa, what's this comment? That doesn't make any sense. No, in a suspicious in the sense that she's suspicious of. I should have clarified that. Thank you. About that the comment was related to the airbag, an issue with an airbag, and so she labeled like 2,000 of these by hand. Yep. Sorry. Yeah.
If you start with such a problem without having any labeled data,
Yeah.
labeled comments,
Yeah. Yeah.
how would you estimate how many do you need to label in order for model to have something to work?
Yeah, I mean that's a good question. I mean it definitely depends on the data set size. If you have like 33,000, right? Because the thing is, if you're training a classifier on and your bias is like you only have a supervised label, and your bias is such that 99.999%, right, of your actual labels are one class, then your training algorithm is going to have a really hard time trying to figure, right? Because you can get really great accuracy just by labeling everything as that, and so it's sort of there's no hard science to that. That's just sort of, the more you can get it to 50%, the better off you are. But in practical experience, you don't really even need to get there. I think for me, I try to go around the 5 to 10% bias. So I have 90% of one label and at least 5 to 10% of another label. So that's sort of my rough estimate. But the more the better. The more balanced, the better off you are. And that's actually a serious problem in a lot of real world problems. Because labels are not cheap, right? So they're costly.
Yeah, the question, I work for IDLE, so that's an API platform that does this kind of stuff. So I was
Oh,
wondering
cool.
if you used
Yeah, I should mention that.
yeah, if you use any kind of platform like Solar or Elasticsearch.
No, I just use scikit-learn. I'm a Python person. I know Vivian's an R person, but I like to use Python. So
So you built your
Okay.
own, so you used your own Bayesian.
Oh, scikit-learn's a package that implements a lot of this logistic regression stuff. I would not recommend actually ever implementing your own logistic regression. There's all these great packages out there that do it for you. You just have to know what you're doing. You have to know why you're regularizing, how you cross-validate, things like that, and then you tend to get pretty decent results.
So
So
then the dictionary of suspicious terms, is that something you used as a input for your search, or is that something you used to categorize your search results?
For those features extraction, I did it all in Python. I think there's something in either scikit-learn or scipy or something like that can featureize and tokenize things from language.
Tokens.
Yeah, I extracted tokens, and then I create a matrix, which was about 59,000 or so features, and then with 33,000 examples. And then you have another vector of ones and zeros, basically saying that this is a suspicious comment or a not so suspicious comment. And that's,
So
yeah.
that part where you label it as suspicious or not suspicious.
That's done by hand. That's manual. Yeah. That's a painful process. And so
You've done
within,
something like sentiment analysis.
sentiment analysis is large. There's a lot of different approaches to that. Yeah.
Can I ask how you dealt with negation of like certain features, like for example, deployed and never deployed?
Yeah. I didn't work on that very carefully. That's pretty much the answer. We only had a few days. So it was one of those things that dealing with deployed and never deployed, you kind of have to sort of either train something to figure that out, or you have to sort of look through by hand and take those things out, which I didn't do. So that could have caused some issues there in the algorithm as well. But yeah, it's a good question.
After regularization, how many features are actually important for the classification?
Good question. I think I have to go back and take a more careful look, but not too many. So that thing I showed you before, right? I mean, you can see that almost a lot of these features start going close to 0. And so, so most of the most important features are sort of pretty much here. I just threshold at some arbitrary nice visual value, but for the most part, you definitely don't come out with 60,000. And that's the nice thing about lasso or L1 regularization, right? Because it promotes sparsity. The other issue is that when you have features that are highly correlated, then you run into this issue where it can arbitrarily push down something to 0 and push something else up. But those are sort of more nuanced things that you can deal with. Yeah. Okay. Great questions. Oh,
What
okay.
did you use for the visualization here? This looks more like R to me.
Oh no, this is matplotlib for Python. Yeah. Yeah, I mean the visualization stuff in Python isn't super great. I know R has ggplot, all these really nice things, but yeah, it's just yeah, it's not too bad. So okay, so this was yeah.
The New York Times, does everybody have their own tool set? They just approach it from, like you pick your own tools to do this project, or you're not
Yeah.
anything?
Sorry, so you mean like if yeah, I chose Python because I mean the data science team at the New York Times is like me, Chris, and Colin. It's like 3 people, and so we have pretty much leeway over a lot of different problems. I work on some of this journalism stuff, but this is like 20% of the kind of machine learning problems I work on there. So it just sort of, because of that smallness of the group, it gives you a lot of flexibility to just sort of do what works for you. We don't have like a whole, pipeline or something. It's not like Facebook or Google, for example. So, yeah. Like I know Chris likes R a lot. So, yeah. Okay. All right. So this was supervised learning. Now I'm going to move into the much harder problem of unsupervised learning, which is when you deal with, which is most of the world's data, right? And most of the world's data doesn't come to you labeled as being suspicious or not suspicious, things like that, right? A lot of times what you dealt with is just a stack of papers, and you have to somehow extract structure out of that. And that's a very, very hard problem. Okay, so this particular problem, I was motivated by FOIA requests, which are Freedom of Information Acts, and a lot of journalists, for example, are really interested in analyzing these documents in a timely manner to extract insights and things of that nature. So I'm going to start talking about topic modeling and making sense of these to make sense of these large document collections. And I'm going to get a little bit more in depth in terms of the math and the modeling and stuff like that. So feel free to stop me if this gets really confusing. Okay. So what are topic models, right? So imagine you have this document in yellow over here. A topic model, what it does is that it sort of tries to decompose documents as and I'm talking about the Bayesian topic model. People sometimes have nuances about it, but this is sort of the standard topic model that a lot of people use, or tends to be this Bayesian version of a topic model. And it decomposes documents as a probability distribution over topics, okay? And what are topics? Well, topics in turn, they represent probability distributions over the unique words in your vocabulary. So let's say I have a document like this. I just sort of made this document up. It's not like a real document, but just to show you an example, a topic model will take all these words, label each individual word as being associated with a single topic, and that sort of can then be represented as a distribution over these topics. And when I say, and I have something like politics, climate change, genetics, and I put that in quotes because what they really represent might be these kinds of word clouds. Okay, so you might have a lot of words that give high probability to words related to politics. You might have words that give high probability to words related to climate change and genetics and so forth. And what's nice about this is that the topics that it extracts have some really interesting semantic interpretation. And it does this without assuming, outside of the model, it just learns this. And that's why they've been so popular, because they've been sort of able to extract these meaningful semantic themes. And then you can also search through documents based off of these themes. So I might say, okay, well, I got this cool topic on genetics. Give me all the documents related to this sort of genetics topic. And then you can sort of think of this as a semantic index of sort that you can learn without just feeding it to some machine, and that is capable of spitting this out. Okay? Yes?
Are you using something like WordNet to get the topic associations?
No WordNet. Yeah, so these topics are just coming out of the model. WordNet is I guess you could use. Well, what were you? How were you thinking of it as a?
WordNet allows you to
Yeah.
not only have synonyms, but also to have different levels of abstraction.
Sure.
Pekingese would be associated with dog, and dog
Right.
associated with animal.
Right.
So you kind of work your way up the abstraction tree,
Yeah,
and
oh.
then you can just use
Okay. Yeah.
the top level as
Sure.
as a topic.
Right, but I don't know how you would integrate that into a topic model, other than taking the topics that are extracted first, and then sort of maybe doing something with the topics themselves. Is that what you're
Just
saying?
take all the words and,
Yeah.
and start getting something maybe 2-3 levels up from those base words.
Yeah,
and then
yeah,
you'll
yeah.
see some commonality of all things related.
So you first take a topic like this.
So there might, let's say,
Mhm.
one document had cats in it, the other
Yeah.
one had dogs.
Yeah,
They would be related to animals,
right.
and so by working your way up, you would,
Oh yeah,
come up
okay.
with the animals as a topic,
Sure.
and group all
Absolutely. I agree with that you can use WordNet to then analyze documents, but
in an unsupervised way.
in an unsupervised way, certainly. That could be one way of doing it. Yeah, this is sort of a different approach,
Okay.
right? This is I'll go into the model specifics, and then maybe we can talk more about whether or not you disagree with the assumptions of the model. Fair enough? Okay. So how many people here are familiar with graphical models? Okay, great. So graphical models are really nice. So when you're like a machine learning person, and especially if you're a Bayesian or if you like to think about things in that way, graphical models are nice because there's a sort of a visual representation about all your sort of assumptions, or a lot of the assumptions that exist for the kind of thing you're trying to do. And so this is the classic graphical model for topic modeling. And so I've just sort of pointed arrows at, is this mouse? Okay, great. Hopefully you can see the mouse. So for example, in the scenario where we have these topics, the topic proportions over documents, this might be represented as a variable called theta d. Okay, and then this particular variable theta d is, from a Bayesian sense, it sort of is drawn from something called a Dirichlet distribution, and that in turn parameterizes a multinomial distribution. So if you know some of these nice properties of these Bayesian sort of models, one of the things is that you have this nice conjugacy. So for example, this theta d is from a Dirichlet, and this zdn is the theta that is drawn from this Dirichlet can then be used to parameterize another distribution, like a multinomial distribution, and then you can then generate z's out of these. And these z's are actually, here I sort of represented this as colored, but you might represent this as the index of the topic. Okay, so a multinomial distribution, if you a sample from a multinomial distribution, you're going to get a basically a count over the frequencies, right, of how a particular integer was represented there. So so you have a multinomial distribution. You have an observed word that's shaded, okay, and these plates represent replication of variables. So you have, for example, n copies of these within a plate that has d copies. So these have d times n copies of this particular word, and d here represents document, and n represents the number of words within that particular document. Okay, so this is a way of just representing how your variables are interacting with one another. And the reason why you want to sort of do this is because when you show this to another person who's a machine learning person, they can look at this and just know immediately what the assumptions are. So I know, for example, that if I know z, then theta is independent of w. Okay, so if all I need is information about z in order to know that there's an independence between theta and w, and this is sort of this conditional independence property that you can sort of visualize in a model like this. Okay, and so your topics here are represented as beta k, and so there's going to be k of these topics. Okay, and so that's so just think about when you're running a topic model, you specify like k is some, you can specify some number, k equals 10, 20, 30. You give it the documents, and then you just give it the number of iterations it needs to run, then it spits all of this out. It learns all of this. So right now the arrows are pointing towards W because the sort of model is trying to express a generative process. So it's saying that once I can start with alpha and I can start with eta, and I'm going to sort of define this generative process where alpha then can generate theta, theta can then generate z, and then z will generate the actual observed words. And then there's this other relationship with beta k and eta as well. Okay, so hopefully that's not too confusing. But this is sort of how we sort of like to think about when it comes to topic modeling. This is how we sort of oftentimes represent it to other people. Okay. So this, yeah.
How is that related to clustering? I mean, the things that you're doing generally,
It's
you
often-
achieve it through clustering and use that.
It's often referred to as mixed membership clustering. So k-means is an assignment of a single hard cluster assignment. For example, if you were to say a document is a cluster 3, cluster 4, cluster 7, with LDA, the name of this model is called latent differential allocation. It was developed by David Bly, and it's basically, you have this idea now of saying that documents are a mixture of clusters, saying it's at 30% of this, 20% of the climate change, 30% of the genetics, that kind of stuff. With k-means, you typically would assign it to something like a single topic. So a lot of these models, you start thinking about mixed membership, which is a much more natural way of thinking about objects that are sort of much more complex. Like a document is typically rarely about a single thing. It's about multiple things in different proportions. I want to talk a little bit about Bayes. Maybe some of you, sorry if this is too easy, but the Bayes theorem, just to give you, because I want to talk a little bit about inference, but Bayes theorem is basically right here. And this is sort of the fundamental part, like if you want to understand how this sort of inferential learning machinery works, you kind of have to understand Bayes theorem. And that's a relationship, just a mathematical relationship, developed back in the day, 1700s, where you have some prior belief about the world, which is sort of, this is what I believe the universe is. You have some likelihood that says, given my belief about the universe, how likely is this particular event? You have this normalization constant that gives you a probability. And then you have, this is sort of necessary to get probabilities for P of A given B, which is your posterior. So now that I've observed some evidence about the world, what is my new belief about the universe? Okay? So this represents the sort of fundamental aspect about a lot of Bayesian modeling. And you really have to sort of internalize this and then so if you think about it, P of A in LDA is essentially all of those random variables, right? P of B given A is the word, the probability of the word given A, which is this very complicated sort of assumption I've made about how documents are generated. And then P of A given B, right, is basically what is my new sort of settings for these sort of knobs, these particular random variables given my data, okay? And then, P of B is the normalization constant. And you get that because when you multiply P of B given A times P of A, you get a joint probability, the joint probability of P of A and B. You have to marginalize over A in order to get this. You don't just get P of B magically. This makes everything a lot harder because that marginalization is extremely difficult. Right, so just to be more clear, if your goal is to obtain this particular posterior, what is the probability of theta z given my words and whatever specific hyperparameters I set? You have to calculate this marginal thing here. P of W given alpha beta. And this is just intractable because there's all sorts of combinations you can have with the way each token is assigned to a particular integer and the way your theta is sort of distributed and things like that. So this is a very, very difficult analytical problem. There's no closed form for it. So all the research, or a lot of the research, I shouldn't say all, a lot of the research, as David Bly, like someone said to me, he said, he said, developing a model takes about a week or two, and then deriving the inference algorithm takes about a year. So that's sort of like, it's like I can draw this on the whiteboard. I can draw whatever I want. This is connected to this and this is connected to that. But to then sort of derive the way to invert that relationship in order to then update everything is not a trivial process, at least in my opinion. A lot of my PhD work is focused on that. But there's for certain types of models and certain types of relationships, a lot easier. And I don't want to sort of I'm more than happy to answer more specific questions about that if you want to, but for now I'll just move on and just to give you the idea that the problem, you have a topic model and the reason why you can learn something is because of Bayes' theorem, and you derive algorithms that can sort of invert that relationship with this generative process going towards the words, and you sort of want to reverse that process. And so conditioned on words, you update z, and then given the value of z, you can update theta, like that, and sort of want to reverse that process. I just want to say one quick thing about scalable learning and inference, because that's sort of what a lot of the sort of new research areas are focused on. So topic modeling, for example, typically when you want to do this sort of learning inferential procedure, you analyze all your documents, and then you then update these parameters once you've sort of looked at all of it. And so a lot of the stuff that's I work on and a lot of my colleagues work on in the sort of academic world is to sort of think about doing this in a smarter way. So let's say we want to analyze a subset of documents and then make an update after that. Can you just do that? Sure, but you have to actually show and prove that that's still going to lead to a good solution. and so it turns out that you can show that if you analyze only a subset of documents and update these global parameters, you can actually get really good results. And this is sort of, when you hear like scalable learning and inference and topic models, a lot of it is based off of this idea of only analyzing a subset of documents and then updating these global parameters as a result of that. Yeah? What's that? Oh my goodness. Oh, sorry. Okay, great. So, okay, all right, so that's just basically how it works. Yep.
Can you talk a little more about that, is when you sort of are grouping together the documents and batches? Because you could see that if you had two bad, poorly distributed batches, which the topics are more heavily here and more heavily here, the results you get.
Yeah, I mean, that can definitely happen. Part of it is the larger your mini batch, you'll probably do a little bit better. But in many ways, actually, given the same number, if you have a time budget constraint where you can have 4 hours of CPU on your Amazon EC2 cloud, it turns out this gives you better results. A lot of times can give you better results within the same time budget if you analyze the same number of documents. And the reason why is because it turns out updating those global parameters more frequently intuitively is a lot smarter than just having to spend all that time analyzing this when those sort of global parameters are initialized at a really poor state, right? When you start this model, you don't really have a really good guess of what those parameters should be. And so if you keep constantly updating them much more frequently with a subset, it turns out that actually gives you much better performance. Yeah. Oh yeah, sure. Hey.
So you mentioned at the beginning that K is an input. So what are the best ways to decide on K? I know there's no science behind that, but like from experience.
Well, I mean, there's a lot of actual work on that. And that's sort of the Bayesian non-parametric world that I spent some time on. So if you have a prior, you can define a prior as this distribution like a Dirichlet. Are you familiar with it? Yeah, okay. So that's fixed, right? That's parameterized at certain K, typically. But instead of using that, you can use something like a stochastic process, a Dirichlet process, and that has an infinite parameter space. And mathematically, you can actually learn the number of K through the inferential procedure. And that's definitely much more state of the art in terms of, but it's actually this toolbox that I'm using for Refinery and all that stuff actually supports it. But there's a whole field called Bayesian non-parametrics where you don't have to actually explicitly specify K. You can actually learn that through the model. And that's using these priors, these stochastic process priors, like the Dirichlet process, the Gaussian process, things like that, Indian buffet process, Chinese restaurant process. These are all these fancy priors that you can use that allow you to do that. But if you don't want to do that, I typically just like look at the number of documents I have and make a pretty good guess based off of that, but it's not perfect. So, you know, if I have 1 million documents, I'll probably do something about 1,000 topics, for example. You know, but it's still like a rough thing. But if you have like 100 documents, you know, you just have to be smart about it and think that like, okay, that's probably like 10 or 20, you know, that kind of stuff. So it's just kind of, yeah, it's a little hand wavy, and there's some really good research that tries to deal with that, but that's not a trivial problem at all, finding the number of K, right? Because that really defines what you sort of discover, right? It's not, and so there's a deep question there as to how you do that effectively.
We use n divided by 2 square root.
Yeah, I guess so. I mean, that's a relatively, you know, reasonable thing to do. One way you can do cross-validation is always you can do things like, for a topic model, you can have a held-out test document and then measure something called perplexity, which sort of looks at how well your model, intuitively, perplexity represents how well your model can sort of compress that information. So you have a held-out test document data set, and is your model capable of sort of creating sort of a really compressed, efficient version of that data set, given the model that's sort of in that state, you know. And then so you can do that and then try different K. And sometimes when you read these topic modeling papers, you'll see a chart where you have perplexity on one thing and you see different Ks. and so you see that k, perplexity is really low, which is good for a particular model version at k equals 48 or something like that. So that's one way of testing out what's a good k, but it's expensive. You have to run your model at every different k level of k, and then that's not cheap, right? So it's not the most effective way of doing it, in my opinion.
So you mentioned that this algorithm that decided K is part of the toolbox that you use. Which toolbox is that?
This is a toolbox that a great colleague of mine, Mike Hughes at Brown, is developing. I've worked on it too, actually. So it's called Bayesian non-parametric Python, and it's we actually have I think the best topic model inference algorithm. Wait, maybe I shouldn't say that I'm being recorded, but one of the best that hasn't been published yet, but it's submitting, and it's a very elegant inference procedure that I think tells you the number of topics and is very scalable, extremely fast. And there's some nuances there as to why it's really good, I think, in my opinion. But we can go into that later. Yeah. Any question? Okay. Great. All right. So let's see. Okay. So here's Refinery. All this topic modeling stuff, you got to run this Python toolbox and get all that. And it's for a lot of people, you guys are probably pretty savvy. But for journalists, when they see things like that, they're just like, okay, I don't want to deal with this. And so I care deeply about journalism. And so one way of giving topic models access to people is to develop a web app, which they can just pretty much load up into their browser and upload their documents, and it just runs it all for you. And it gives you a nice visualization. So this is a project that was funded by the Knight Foundation. I don't know if you guys are familiar. The Knight Foundation is a journalistic media innovation and philanthropy. And basically, Ben, who's a colleague of mine, he's also another PhD student. He graduated in the MIT Media Lab, and myself, the two of us worked on this for a long time to develop this nice, and so we sort of had to become full stack web developers in order to create this. But it's using d3.js and allows you to sort of it extracts these topics and it creates a nice sort of concentric ring where the sort of proportion of each ring tells you how much of that topic exists within your whole corpus, and then you can hover around it and sort of select topics, and then from there you can actually select documents related to those topics, extract phrases, sentences. There's a bunch of stuff that we built into this with the hopes of constantly iterating on it to help journalists and stuff like that. Okay, so you can check it out at docrefinery.org. Let me see. Right, so this is the stack that we built. It uses a whole, it's all Python. It actually uses the Nginx Unicorn Celery Flask. It's all built off of Python. It uses Redis and PostgreSQL for the databases. It uses BNPy, which is the Bayesian non-parametric Python toolbox. It uses d3.js as an interactive visualization. And it actually, developing a web app like this is really complicated. So installing it was an extraordinary challenge. So people who don't know how to work with software, to install all of these things would just be too much for any journalist or anybody who wants to use it. So we actually have it now. So you can just git clone this repository. You install Vagrant and Oracle, the VirtualBox, which are free. You can just install it. They're just these apps you can install. You just type in Vagrant up, and then it'll download everything, configure everything, provision everything, and then you just go to this address, and then you just open it up. Okay, so if you want to ever, feel free to try that. Git clone it, Vagrant up, and then you have a working topic model, basically, that you can just that creates a virtual machine inside your computer, and then you can then run topic modeling on that. Okay? Great. So the typical pipeline for something like this is you just upload a bunch of documents, you extract topics. This is one pipeline. You don't have to do this and yep. It's this one here, github.com/dalekim/refinery.git. So it's my name. And Refinery, R-E-F-I-N-E-R-Y. Okay. Great. So this is a typical pipeline. You have you upload your documents. You can extract topics via topic model, and then you can find a subset of documents that are of interest to you. And this little thing I added here is another thing where you can actually extract phrases, sentences. So it turns out, extracting sentences from your documents is not that trivial. So we use a SVM to train a classifier to figure out what a sentence boundary is, and then we extract phrases that way. And so you have these nice little phrases, and then we have a system of extracting phrases and then you can select a bunch of these and then find other sentences within your document corpus that are similar to the phrases of interest. So one way of using it might be, well, I found this really cool topic. I want to get all the documents related to that. I run this sentence extraction thing, and I find a bunch of phrases I'm interested in. I look for things that are similar within that particular subset. That's one way of doing it. And so I'm working with people at the Times to try to improve and iterate and try to cater to the sort of things they need. But really, the problem of dealing with large document corpuses applies to everything. A lot of different types of problems, like e-discovery, like law firms who get these big data document dumps and they want to analyze and understand what's sort of in there. And Refinery is completely free, right? It's like totally, it's private, it's local. Right, you don't have to upload documents on a server, which was a big issue. Like, and when it comes to journalists, they want their document collections to be private. So one of the things that was important was to make sure you can just download this and just run it on your own machine and things like that. So that's sort of the motivation there. So if I had my computer, which is now just not working, I was going to show you a demo of Refinery. If you git clone the repository, maybe somebody else can start running it, but there's part of the repository, I have a bunch of articles from the New York Times with the word Obama in it. And so from 2013. It's about 500 documents, and one thing I was sort of curious was like, oh, okay, so what did the New York Times care about when it came to Obama in 2013? And you actually can these are actual topics that were extracted. So there's stuff about Bloomberg here, there's stuff about Syria, and there's stuff about Netanyahu and Israel and things like that. So those are just 3 example topics that the model discovered, and you can kind of see that from these sort of word collections, there's some semantic coherence in terms of what those words represent. And that's sort of what I think can be useful for people.
You compared result with word cloud?
With what, sorry?
Word cloud.
Word cloud? What is that? Sorry, I'm not aware of it.
It's a package in R.
Oh, okay. I don't use R, I'm sorry. Yeah. Yes?
Aren't the documents, aren't they scanned, and don't they have a lot of redaction? And I mean, how do you get from scanned documents to text that can be interpreted by your program?
Oh yeah, that part is not, so that Refinery doesn't have that. That's not what it's, so there's other tools out there.
Mm-hmm.
So, the OCR process is not trivial, right? Google has Tesseract, and it assumes for the most part that you have documents pre-processed in a way that's clean. So there's actual text there. But if you want to, which is a very important problem, but we're not trying to deal with that because there's a lot of things that you kind of have to, there's a lot of work in dealing with that particular thing. And a lot of other people are doing a good job with that. Google, some documents are really difficult to OCR, but what can you do, right? So, anybody else have it? Yep.
Do you go beyond the topic model as far as processing information linguistically?
Oh, so like once you extract topics, do you do something else on top of that?
Yeah, do you like a flat model to figure out more about the documents linguistically?
Yeah, I mean, topic models will give you this. Whatever you want to do with the topics on top of that is sort of a secondary step. If you want to look at, for example, the structure of the language, so if you want to, look at parse, you can parse a sentence, for example, and extract something called a, PCFG, a probabilistic context-free grammar, which is like a tree-structured representation of a sentence, starting with like sentence, noun, verb, phrase. You can extract those kinds of things. This doesn't do that. That's sort of another NLP different kind of problem. But this is what a topic model can give you. It gives you a sense of what your document corpus is about, but it doesn't answer all the questions, certainly. So
when you get these topics, is there any good technique you have for pulling out some kind of like the best keyword to describe this topic? And then the follow-up for that is, do you have any like evidence that like if you do some training or whatever, you see that if you had a human being that would label the article with the topic that indeed that this is doing a good job in some sense?
Yeah, that's definitely a good question. I mean, you can. I mean, you can set up a system that way to validate a topic model. There's some work out there that tries to validate the goodness of a topic through like crowdsourcing and Amazon Mechanical Turk and stuff like that. No, my focus is mostly on doing the best it can with whatever sort of modeling assumptions there. So, if in an ideal world, I mean, you have to understand this is not the inference, the learning that happens in the topic model. Depending on how you initialize and how you specify things, you get different results, right? And so, I mean, certain topics will constantly reappear, but it's not like because the optimization problem is so difficult, you're never going to sort of always you can't. It's NP hard in computer science terms. Like it's not trivial. So, yeah. Okay. So, yeah, so Vivian, I'm sorry. This is I thought it was going to be like an hour talk, but this is
No, please use the full 2 hours.
Right. No, it is. It's only an hour talk. Sorry. So, but we can ask more. You can feel free to ask questions and things like that. But I thought this was yeah. But then I just want to talk some about future directions. And so, like you said before, like is there a way of creating tools to filter and clean data? And I look at that as so if you want to do investigative reporting, those are 2 crucial steps. And then sort of where Refinery and topic modeling comes in is sort of extracting some insights once your data set is clean and optimized. So if you heard of Document Cloud, it's a great organization, also funded by the Knight Foundation. It was a Knight News Challenge winner, and it actually acts as a repository for all these sort of primary document sources that journalists might be using and collects them. So you can actually pull documents from that, and they do the OCR process and cleaning and filtering there themselves. So and so Refinery is a way to sort of fill in the 3rd step. How do you extract insights once that happens? Okay. I guess I have one more slide. Yeah. So I guess I want to just talk about this real quickly, and this is sort of a, but topic models can be extended. You don't have to just stick with that. There's all sorts of extensions you can do, and it's just sort of, it really can get into some really interesting questions and ideas about how you want to model something. So here's an interesting extension to topic modeling, which is to incorporate topic models with recommendation systems. So this is a problem that is of interest to the New York Times because not only do we care about giving you guys good recommendations for articles, but we also want to analyze the articles themselves. So you might have, you have ratings and you've read certain articles that you like, but there's also stuff about the articles themselves that are of interest. And we want to sort of both incorporate ratings and the article content to then create a system that can sort of provide you with even more insights and better recommendations. And so this is something called a collaborative topic model. So you have the LDA portion of the generative process, but then you have this other portion that also models ratings and recommendations as well. And you can incorporate that, and some of the nice things is that you can then discover users, and you can decompose users as being a mixture of topics. So users about maybe into horses, it might be into cars and things like that. And you can actually learn that the hidden latent representation about each user based off of what articles they've read, the content of those articles, and the ratings themselves. And what's nice about these Bayesian models is that the stuff you discover is interpretable versus something like a deep network, which are very powerful, and don't get me wrong, they're amazing for things like supervised learning as well. But the features you extract from and the way it does it is sort of hard to sort of comprehend versus something like this, which actually has some like meaningful interpretation. Okay? All right, so that's all I had for the talk. Feel free to ask me questions and feel free to just sort of, go and yeah. So that's it. Sorry. Yep.
Yeah. So the airbag question and story was really interesting.
Sure. Thanks.
Was that just kind of a test case that you used to start to prove out that this is something that Times can do, or is this something that you use frequently with investigative journalists? No.
This was more of a test case.
Okay.
It's a good question. It's because I mean, a lot of journalists are not. Like there's machine learning is still new to some journalists, and so part of it is sort of me trying to go and then being like, hey, you can use machine learning for really cool stuff like helping your investigative journalism, and that's really the thing I care a lot about. I care a lot about taking a lot of these tools and to sort of make journalism a lot easier and a lot faster and a lot better.
Have you tried this very approach on some other cases which are less annotated than airbag?
Less what? Sorry.
Annotated.
Less annotated than airbags. So, what could you give me an example, maybe?
Like any other case which with smaller number of labels.
Yeah. Well, I mean, you can still do the same thing with a smaller number of labels. The number of labels just determines how good your result's going to be.
Exactly.
Yeah.
That's the question.
Yeah.
How good the results will you get?
It's a hard question because it really depends on understanding the data. So if your data is really noisy and your documents are really noisy, and you might not really get anything interesting. If it's clean and you have some interesting patterns that exist there, then you might. So it's hard. It really depends on what data you're working with. So, yeah.
How general is LDA? How short a document can you run it on and expect meaningful results? I'm thinking tweets.
Yeah, tweets. That's a good question because oftentimes with tweets you only have a certain number of characters and you don't really have. And so what sometimes people do is they aggregate. I mean, it matters. It does matter how if it's really short. If you think of each tweet as a document, you're trying to say that this is about 5 or 6 things or 10 things. I mean, it's kind of hard to say that. So what people do is sometimes they'll aggregate tweets, and they'll say a person is a document, and all the words that the person says can be thought of as a document, and you have a lot more words there, and then you sort of decompose that. Yeah, but that's something you have to consider depending on how short or long the document is.
Yeah, how did you generate your training set? Do you hire a bunch of Indian freelancers to assign topics to that paragraph?
The training set? So this is unsupervised, so you don't need anybody to label anything. You could just download whatever PDF or documents. In the supervised setting, where you have to, I mean, that's the process of who you want to get to label that stuff, which is not cheap. So, yeah.
How do you, so in the topic analysis, what is the role of this kind of process in trying to identify bias in the corpus as well? So, for example, when you, in your example where themes around Obama. That's also a reflection of like the pool of articles from which you're pulling.
Sure.
If it's the New York Times, there might be a certain slant there, over time.
Oh yeah, definitely.
Washington Journal.
Sure.
Just curious about, obviously, topic modeling right now is inward looking. Your thoughts on the role of machine learning in exposing bias also with corpuses.
I mean, if you have a topic that comes out that talks about, you maybe have a topic that comes out that's like health, and then and positive words on that. I mean, then maybe you can sense a bias, but it doesn't really try to I mean, you can sort of see that maybe there's a bias in the sort of topics that are covered in general. So, for example, certain very conservative websites might focus on certain issues that are very of their interest versus more liberal sites that might focus on a different type of issue. So it's something that's something where topic modeling can help, but I think you kind of need to do more things like sentiment analysis or apply sentiment analysis algorithms to figure out maybe more of the sort of whether that bias is conservative, explicitly conservative, or things like that. Or there might be some things you can do there, but I'm not sure if you can just use a topic model and then immediately get a sense for what. I mean, maybe you can. It's a qualitative thing then at that point for me. Yeah, if you were to use these topics. It's not built into the model.
It's hard to believe data scientist team only have 3 people in New York Times.
Yeah, there's only 3 people, but we're getting somebody else, but it's I mean it's a small group. It's a very small group. Yeah.
What about that line of questioning? How do you manage doing a full-time job and a PhD?
Oh yeah, it's suffering. It's suffering. Part of it is I mean you get to work on some of these problems that are. So one thing I can work on is I can develop a better, model, so that's scalable and stuff like that. So Dave Bly, he's on my PhD committee. We work together. So we'll try to sometimes think of a problem where we can then apply it to something relevant to the Times as a way of combining efforts. But typically, you just have to. I'm in my 5th year, so I'm almost done. So I'm pretty much gonna, finish pretty soon. So hopefully, yeah. So.
Can you talk more about the New York Times and machine learning?
Mm-hmm.
Like what are others are doing? How did it New York Times start dealing with it? Is the connection to the visualization team?
Oh yeah, yeah. I mean, we have a great I mean, the person who invented D3 is at the New York Times, Mike Bostock. The guy who, so there's a bunch of really talented people there. In terms of machine learning and journalism, I look at it more right now as a way of helping and assist journalism. We're not really generating stories, or at least that's sort of not the focus right now.
All of you doing the same thing, basically?
All of us, who do you mean by all of us?
Learning.
The group, the data science group?
Yeah, you have a 3.
No, I'm really the only one that focuses on the journalism side. Yeah, most of us focus on the business side of things and optimizing a lot of the business problems that are currently there. Yeah.
Okay. Last question.
Can you talk at all about open journalism at New York Times, like sharing code or sharing data behind stories?
Yeah, definitely. I'm more than happy to share any code I write. New York Times is pretty good about that. For example, their Senate forecast model. For example, all that code is shared. It's written in R, and you can actually download it and run it yourself. So the New York Times, when it comes to open source, they love open source, and they love being able to share that code and being able to do that. So, yeah.
No more.
We can chat,
okay.
afterwards.
So can we organize hackathon like using the code you guys published?
A hackathon?
No, like teaching people how to use their open source code you guys released.
Oh, Refinery.
Yeah.
Yeah, so there's a video demo on the website that you can just look at, and then you can also just email me and ask me questions. I don't know if like organizing a hackathon is really worth your time, but it's definitely, you can download it, and it's really easy to use. And I have a crude video demo of how to use it. I just wanted to get something up real quickly. So that's sort of and it's really just simple to use. It's not very difficult versus like trying to figure out all the commands and stuff for a particular package.
Okay. Is it on YouTube?
Yeah, it's on YouTube. You can go to the website docrefinery.org. So it's I can send you these. I think I have it here. Yeah, this is on the bottom here. Sorry, I'm not very good at selling this, but it's docrefinery.org. You can check it out, and this is the GitHub repository. You can just clone it and access it. So
cool. I think half of you know my tradition. In the very end of the meetup, we will have the moment of truth. We will vote for tonight's speaker. If you think he's awesome, he's super awesome. He sucks. We shouldn't invite him back. So, can you come here?
Okay, yeah, sure.
Just turn it on so they don't feel pressured. Please.
Okay.
A little bit.
All right. Here, I'll just sit here. How about that?
No, you are the speaker. You have to be in the middle. So we know you are responsible for tonight.
Okay, sure.
Okay, guys, please vote. Be honest, so I know who I should invite. You look like you're guilty. Okay, like one more. Everyone is voting. You can do both hands if you like. Awesome. Thank you. So, I think 99% of people vote for you this way.
Oh, great.
So, thank you for the night and put so much effort.
Thank you.
And can you believe this is his first ever meetup?
Yeah. So yeah, and I'll be around for a little bit. So if you guys have any particular burning questions, I'm more than happy to answer them.
So I just want to say, if you want to try the word cloud, you can search word cloud in my website. Well, my student actually scrape the data from Twitter and generate the word cloud. So if you search Twitter, you will find a post with all the code. So analyzing tweet trend with Twitter R and the word cloud. So it will look like this, the main topic. So you can try it out.
Hopefully, yeah. Great.
Cool. Also, I'm looking for an awesome speaker. If you have specific things to share, please talk to me. Thank you.
Can I give this to you?
Yes.
Great. Thanks so much.
Good talk.
Oh yeah, thanks.
Actually chatted with Chris Wiggins once.
Oh really?
Great. It's a lot of